T Coronii Borealis, also known as the Blaze Star, is on the verge of an extraordinary celestial event. This rare nova eruption, caused by the interaction between a white dwarf and its red giant companion, has astronomers and skywatchers eagerly anticipating a spectacular display. With a history of dramatic outbursts and recent signs of increased activity, TCRB offers a unique opportunity to deepen our understanding of stellar evolution. Scientists initially predicted the eruption might occur by September, yet months later, the star continues to build toward its explosive moment. So, what's causing the delay, and why is this event so significant? In this video, we'll explore the history of TCRB's eruptions, the latest discoveries, and the challenges of predicting when this remarkable nova will finally ignite. The first recorded eruption of TCRB in 1866 astonished the scientific community when the star suddenly brightened from a faint 10th magnitude to an impressive 2nd magnitude, briefly matching the brightness of Polaris. At the time, astronomers had limited tools to investigate its origins, but this unexpected event introduced the concept of novae, explosive outbursts on white dwarfs. 80 years later, in 1946, the nova erupted again, reaching a slightly dimmer 3rd magnitude. By then, advances in observational astronomy had revealed that the white dwarf's explosive activity was fueled by material drawn from its red giant companion. This discovery led to the hypothesis of an 80-year eruption cycle, positioning TCRB as a prime candidate for studying and predicting future nova events. Historical records suggest that TCRB's eruptions may extend even further back. Researchers have uncovered potential references to similar events in 1787 and as early as 1217, offering a centuries-long timeline of its activity. While these older accounts are less precise than modern observations, they highlight the long-term significance of TCRB as a natural laboratory for studying stellar evolution. What makes TCRB particularly fascinating is its predictability on a human timescale. Unlike most novae, which erupt unpredictably over millennia, TCRB follows a cycle short enough for multiple generations to observe. This predictability has heightened anticipation in recent years, thanks to new astronomical observations. Astrophysicist Elizabeth Hayes, who monitors TCRB using NASA's Fermi Gamma Ray Space Telescope, encapsulates the excitement. "We know it has to happen, we just can't pin it down to the exact month." Since 2015, TCRB has exhibited behavior reminiscent of the years leading up to its 1946 eruption. Episodes of brightening have closely mirrored patterns seen 8 years before the last outburst, suggesting an accelerated timeline. Initially predicted to erupt in 2026, newer observations led astronomers to revise their expectations, moving the forecast as early as 2023. Adding to the intrigue, in March 2023, the system entered a dimming phase, similar to the one observed before the 1946 eruption. This pre-eruption dip could indicate growing instability as the white dwarf nears the critical mass required for a nova event. Unlike in the past, modern astronomers now have advanced tools to monitor TCRB in unprecedented detail. Instruments like NASA's James Webb Space Telescope and Fermi Gamma Ray Space Telescope are capturing data across multiple wavelengths, something that was impossible during the 1866 and 1946 eruptions. Observations in gamma rays, X-rays, optical and radio wavelengths are providing a comprehensive picture of the system before, during and after the nova. "This is the most important time," Hayes explains. "We're gathering the best dataset ever on what a nova looks like before it erupts." These continuous observations are allowing scientists to refine their understanding of mass transfer dynamics, bringing us closer to unraveling the mysteries of stellar evolution. While the TCB 80-year cycle provides a general framework for predicting eruptions, the precise timing remains uncertain due to a variety of unpredictable factors. The most significant of these is the fluctuating transfer of material from the red giant to the white dwarf. The red giant's mass loss rate varies due to internal changes, magnetic activity, and tidal forces within the binary system. These fluctuations directly impact how quickly the white dwarf accumulates enough material to reach the critical mass required for a nova explosion. Complicating matters further is the exceptionally close orbital separation of the two stars, just 0.5 astronomical units, or half the distance between Earth and the Sun. This proximity leads to intense gravitational interactions, shaping both the flow of material and the stability of the white dwarf's accretion disk. The disk itself is highly unstable, with occasional disruptions that can either accelerate or delay the nova process. Another challenge in understanding this system stems from the lack of comprehensive multi-wavelength data from previous eruptions. The 1866 and 1946 outbursts were primarily observed in the optical spectrum, leaving significant gaps in our knowledge of the system's pre-eruption state. Today, modern telescopes are working to bridge these gaps by capturing data across the full electromagnetic spectrum. This approach has the potential to transform our understanding of recurrent novae and their crucial role in stellar evolution. One of the most thrilling prospects of this research is the opportunity to observe a nova ignition in real time. Capturing the exact moment when the white dwarf's surface ignites will provide unprecedented insights into the physics of thermonuclear explosions. These discoveries could also help unravel the broader role of novae in enriching the galaxy with heavy elements such as carbon and oxygen. As astronomers continue to decipher the complexities of TCB, anticipation only grows. The challenges of predicting its next eruption highlight the intricate dynamics of binary systems while also showcasing the remarkable progress in modern astronomy. Thank you for joining us on this journey through the fascinating story of T. Coronii Borealis, also known as the Blaze Star. Its next eruption will be more than just a celestial spectacle. It could unlock new cosmic secrets and deepen our understanding of the universe. Stay tuned and keep your eyes on the night sky. You just might witness history in the making.